let's do this example that I was thinking about. So in some manufacturing environments, there will be a person involved in the process that has to do something like pull wire off of a spool, okay? And the human interaction with machines it actually creates a lot of really interesting problems because they're not as predictable as machines. And it brings into the conversation things like, well, what if the person pulls too hard and snaps the wire or plastically deforms the wire? And then, that can enter into the manufacturing process as like a flaw that happens later on in the process or something like that. So in this instance, there was a manufacturing environment, and they had people pulling thin wire off of spools. And what they wanted to do is put a motor in the spool, or on a shaft with the spool, so that it would assist the person pulling. It would keep the cable or the wire at a constant tension. So if you backed it up, it wouldn't slack. It would maintain a nice tension, but it wouldn't be too high. It would be a tension that was low enough not to plastically deform it, and it would keep it from snapping, and it would keep it from going slack. So this was an application in a manufacturing environment that is conducive to the type of analysis that we would like to do. So I thought we would model this, and what they wanted to do is they wanted to say, okay, I want to have a constant tension. So I want to control for a constant tension as the person pulls it. At whatever speed they decide to pull it at, right? I mean, they might decide to pull it fast, pull it slow, or back up a little bit. So they want to maintain a constant tension. And you need to have a model of this first, a mathematical model, before you can design a controller for that feedback loop. So what we're doing in this class is developing that model. Then later on, you would take, you'd have measurements like a sensor, and you'd feed it back, and you would say, okay, am I correctly controlling this so that I put the right voltage into the motor when certain inputs are as they are, or certain sensor values are what they are, to get the tension that I want. So the first step is to get a model, and this looks something like there being a motor with, say, a voltage source connected to it. And a shaft coming out the side. Let's say there's, a bearing on here. Probably needs to be a bearing on the other side of the spool too, but we'll just put in a bearing there. We've got a spool. It's got the wire on it wrapped around, and say coming off this side, and then you've got somebody pulling on it with some force, Fs. Say the motion here is x. They move it, and you have well, we could draw another bearing over here if we wanted to. I mean, you definitely want another bearing on the other side of this spool. Okay, so this is our situation. We are eventually going to measure things like the rotation of the shaft. You could do that by using an encoder on the motor, and potentially other parameters. You might want to measure the torque in some way, or measure that. That's probably the only other variable that would be easy to measure, or relatively so. So we've got this physical system, and we would like to come up with a state space model for it. Okay? From a state space model, we can find a transfer function. The transfer function is actually what we would want to put into that control system feedback loop, most likely. We would do some controller design based on the transfer function. But as we know, once we have a state space model, we have all the transfer functions from all the inputs to all the outputs, so we'll be in good shape. And yeah, so let's just go ahead and draw a linear graph model for this. We've got our standard sort of motor model here, where we've got a voltage source, Vs, and the resistance of the windings, so DC motor model R, the inductance of the windings L, and then we have this interaction with the mechanical side. So here's our transformer that models our motor. We'll call the electrical side side 1. I'm going to move this over a little bit. Just going to have a few things coming down from that. And this side 2. And this is a transformer because it's a motor, right? And we'll call the motor constant, the transformer ratio for it, the motor constant Km. Okay. Now for the rotational side of this, the rotor of the motor has some moment of inertia. There are internal bearings for the motor and external bearings. Let's say that we take the motor bearings and the external bearings all to be represented by one damping coefficient B. We are probably going to have to, individually look at the damping in the motor, look at the damping of each of these, and then combine them to a single damping ratio, or a damping coefficient. But for our purposes, we know we could do that. They all have the same velocity, right? We're not going to assume that this shaft is long and flexible. We'll assume that the rotor has the same angular velocity as the spool, which has the same angular velocity as these bearings have too. So we'll say there's one damping coefficient B, and the rotor moment of inertia can be combined with the moment of inertia of the spool. They're all fixed together, right? If you drew two different J's, you would want to combine them into one anyways. So these are just parallel to each other. So let's just put one moment of inertia J. That's the combined moment of inertia of the rotor, the spool, and maybe the negligible amount that the shaft contributes. And then we have our interaction of the spool with the translational mechanical side. So the rotation to the translation, that interaction can be modeled here. We'll assume that this wire is inextensible. It's not flexible. In certain instances, you might need to take that into account, but we'll assume for now that that is a wire that's not going to be stretchy. And there's going to be some relationship between these two sides we should figure out now. So let's go ahead and do that. We already actually looked at a spool before, right? We saw that the distance x that it moves is if we take theta to be this rotation here, then x is equal to r, where r is the diameter of the spool, times theta. Okay, that's the arc length that is swept through by theta, and at radius r. And if we take the time derivative of this, we get that the velocity is equal to r omega. The velocity here is on side 2, or we'll call this side 3 and side 4. So it'll be velocity 4 equals r omega 3. And this tells us there's an across variable related to an across variable. So is it a transformer or a gyrator? Transformer. Transformer. And what is the transformer ratio? The transformer ratio is 1 over r, right? So it's 1 over whatever is here. And that means that we have the other equation, the kinetic equation, comes for free. F4 is going to be negative TF times the torque 3, which if you plug in the TF is 1 over R, you get negative 1 over R, torque 3. Or we can just leave these two equations as TF, which is totally fine too. So we'll do that. We'll just say this has some TF that we found. It's 1 over R, and it's a transformer. And on the mechanical side, we're just going to say there's a force that's applied. That's the way that we're going to model this. So there's a force, and it's in the direction of the coordinate arrow for x. So Fs is pointed towards the node of application. And we are good. We have our linear graph model. Okay. Normal tree will be next. So 1a is the normal tree. And I'll use green here to denote the normal tree. We take across variable sources, all the nodes, right? Across variable sources, there's one. Fs is a through variable source, so we do not take it. Then we have A-type energy storage elements. So J is next. And I don't see any other A-types. Then we go down to the transducers. These are both transformers, so exactly one edge from each of them, one side of each of them needs to be selected. If you select the side that's connected to J of either of them, we create a loop, right? And we'd prefer not to do that because we would like J to stay as an independent energy storage element if possible. So we can take this one, no problem. And we can take this one, no problem. And we are good there. At the end, we have to check to see that we've selected as few as possible T-types, which L is our one T-type. So we don't want to select L into our normal tree. And in fact, selecting the edge 1 here allows us to select, for D-type, select R here and not select L to reach this node. So that checks out for us. That's what we want. As few as possible of the T-types in our normal tree. So now we've got our normal tree. There's nothing else that we can select without creating a loop. And so we're good. Normal tree. Okay, so now we've got our primary and secondary variables. So primary variables, to keep track of it, it's hard unless you go just like element to element on here. So I'll just follow the elements along. We're looking for cross variables on branches and through variables on links, right? So cross variable on branches, VS, VR. Through variables on links, IL, V1. Now we're on the mechanical rotational side, so we've got T2, TB, through variables. And then omega J, cross variable because it's a branch. 3 is a link, so we have T3. 4 is a branch, so we've got the cross variable associated with it, which is V4. And then the link FS. So the opposite of all those is IS, IR, VL, I1, omega 2, omega B, TJ, omega 3, F4, and VS. All right, so C, state variables. We're looking for A-type branches. J is our only A-type branch, so it's a cross variable as a state variable, omega J. I'm looking for T-type links. L is a T-type link, so its through variable as a state variable, IL. And there are no others. Okay. So now we're ready for our vectors. The state vector is omega J and IL. The input vector, we have two inputs, right? The voltage source, VS, and the force source, FS. And inputs, or outputs, thank you. For outputs, let's look at three things. Let's look at the force. Let's look at the force source. That's the force. We're going to want to look at what's happening with the force source. Let's also look at the torque and angular velocity. So the angular velocity of 3 and the torque of 3. Eventually, we're going to want to put this in a feedback loop where we're controlling one of these variables, and so that's why I'm going to take a look at all three of them. Yeah?
Technically speaking, if you were going to add numbers to this, wouldn't you already know what FS is?
Mm-hmm.
Okay.
So, you're right. It's just the output is going to be just Fs equals Fs, because Fs is an input. So we're just passing that one through, because it's going to be interesting to us because we're going to just try out different Fs values. And you're right, an input is always known. So you're not going to learn anything new with that one, but you're going to compare it to other things that you're going to get out, like the torque and the angular velocity. Good. It might be better to put in F4 here. They're going to be equal, but yeah, that might be a little bit better. Good. E. So we have our elemental equations. And we'll also do our continuity equations and our compatibility equations. So elemental equations, passive elements. We'll put the two energy storage elements at the top. Okay, so the two energy storage elements are L and J. So we'll put J, L, and then we'll put the other, so R and B are the other two besides the transducers. So R and B. And then we have the transducers, 1, 2, and then 3, 4. So the elemental equations, I'll use primes for derivatives. Omega j prime equals 1 over j tj. IL prime equals 1 over L VL. VR equals IR times R. This is a rotational damping, so TB equals B omega B. Now, the 1 and 2 equations are the motor, right? The motor equations are, the across variable one is omega 2 equals 1 over, the transformer ratio for the motor is Km. 1 over Km times V1. And the other equation is the torque 2 equals negative Km times the current 1. 3 and 4, we already got that relationship up here, right? For V4. So we have V4 equals 1 over TF, where TF is 1 over R, times omega 3, and F4 equals negative TF times T3. So those are the elemental equations for each of our elements. Continuity and compatibility equations then. Let's do the continuity equation, compatibility equation as each one arises as we go down the list so we don't forget any. So I'm just going to go J through 4 and do the continuity equation if it takes a continuity equation, or the compatibility equation if it takes a compatibility equation. So J is a branch, right? It's in the normal tree. So it needs a continuity equation. This contour will work. Since the torque through J is leaving that contour, it has to equal all the torque going into the contour. And they all happen to be leaving the contour, so they're all going to be negative on the other side of the equation. So we'll get that Tj equals negative T2 minus Tb minus T3. For IL, for L, we're going to have a compatibility equation required. So VL is going to equal, if we put it into this loop here in the normal tree, so this loop says that VL equals negative VR plus VS minus V1. So it's a compatibility equation, and it says VL equals negative VR plus Vs minus V1. So for R, it's in the normal tree. It's a branch, so we needed to do a contour. That contour works. So it says that IR, which is going into the contour, has to equal everything going out of the contour, which is IL, right? So IR equals IL. For B, it is a link, so if we put it into the normal tree and create that loop, we get that omega B equals omega J. So that's a compatibility equation. Omega B equals omega j. Okay, now we're at the 1 and 2 branches. So the 1 and 2 edges. So the 1 is a branch, and we would say that all of the current going out is so I1 equals all the current going in, because it's going out. So IL is going in, so we have I1 equals IL, which is a continuity equation. For the 2 equation, it's a link, so we put it in this loop with j here, which just says that omega 2 equals omega j. And 3 and 4, so we see that 3 is a link. Once again, it creates a loop with omega j, so omega 3 equals omega j, another compatibility equation. And finally, for 4, we have another branch, so we do the continuity equation for this contour. Since F4 is leaving the contour, it has to equal everything going into the contour, which is Fs. So F4 equals Fs, which is a continuity equation. Yeah?
For the omega 2 and omega 3, it is technically possible to use other omegas besides J, correct?
Anything's possible. This procedure would say no. This procedure would say you want to write omega 2, omega b, and omega 3 all as omega j. Because when you go through this, you put that link into the normal tree momentarily. It creates a loop. That loop says that omega 2 equals omega j. It's also true that omega 2 equals omega b, and it's also true that omega b equals omega 3. Those are also true, but they're not the equations that we're looking for.
Okay.
Those would be true statements that are not useful for this construction. They would be extra equations. They're not linearly independent equations. So you can write a lot of continuity equations and a lot of compatibility equations for each problem. If you follow the procedure, though, you only write the ones you need, which is nice. Otherwise, you get extra equations. Yeah?
Sometimes you draw different contours rather than just the immediate one. You include other nodes.
Yeah.
Is there a reason why you don't do that for, say, branch 1?
Yeah. So for this guy, like you could
I guess for that one it would be because you might include the edge that's not included.
yeah, so you don't want to intersect any other branches that show up. So you don't want to intersect R, and you don't want to intersect VS. So that's why I chose this one. What happens sometimes is that your linear graph or your normal tree has got, say, 2 branches here, and you need to know, and then it's got like a link here. And you need to write the continuity equation for this branch. So you can't do this contour because it would intersect another branch. So instead, you have to do this contour because this one just intersects a link. Yeah. So that's why you oftentimes it's just the node. Like in this case, we just wrote 4 node equations, right? But occasionally you'll want to do a contour that includes multiple nodes. Okay, so these are our equations, and we can do these substitutions, right? That would be the next step. For the transducers, sometimes we have to cross these over. Like I1 goes there, omega 2 goes there, which isn't too bad. Something to note, though. So what I did is I put this into the statement website, so statement.stmartin.edu, and what I did was I just plugged all this in. I should have uploaded a photo of the linear graph, but instead I uploaded a photo of my face because I didn't have a picture of the linear graph yet. I put the input variables in, Vs, Fs. The state variable elemental equations, to skip doing the algebra myself, I use the website to do it. So I have to input the state variable elemental equations, which are the elemental equations associated with the time derivatives of the state variables. Okay? So those first two that we wrote, for J and L. And then the other elemental equations are all the rest of these, R through 4. Then the constraint equations are the compatibility and continuity equations. Okay, so I just went down and just wrote those all out. The gotcha here, though, is that you have to write the constraint equation, or the elemental equation. So we already write our constraint equations with the secondary variable on the left-hand side, right? What we have been a little fast and loose on is that we're supposed to be writing our elemental equations with the primary variable on the left-hand side. So if we go down the list and look at this, our omega j and IL, they're state variables, so they're always going to be primary. So IL, omega j, those are primary. VR is primary, so it shows up on the left-hand side, so we accidentally got that right. TB and omega b, TB is on the primary list, so we're right there. For 1, omega 2 shows up on the left-hand side. So we look up here and we see that omega 2 is a secondary variable. And we should instead have V1 on the left-hand side, which is a primary variable. So we should solve this for V1 equals Km omega 2. And for this equation, T2 is a primary variable, so it's okay. So this one needs to be flipped. I'll do that. Flip this one. 3, so V4 and F4 are used next. V4 is a primary variable, so that's correct. F4 should not be, it's a secondary variable, so we should solve instead for T3, so we should flip this one. Now, the reason that's important, we know when we went to do this substitution here, F4 shows up on the left-hand side. We would have just been like, oh yeah, okay, the secondary variable is on the left-hand side. No big deal. When you're doing it by hand, not a big deal. The computer, though, even the Python script in the background, doesn't know. It actually deduces what the primary and secondary variables are from your list. Okay? So you have to write them with the elemental equations with the primary variable on the left-hand side. So you'll see that for this 4 equation here, I solved it for T3 before I plugged in. So T3 equals -1 over TF F4. And if you don't do that, it'll say it can't solve the equation. So if you put them in correctly and then you hit calculate, it'll come up with this set of state, so this state space model. So the state equation and the output equation. And you can get it in, you can also have it give you the transfer functions, the transfer function matrix as well. So instead of having to do that CSI minus A inverse B plus D, it'll give you that. And you can also copy it out, like if you're going to put it into MATLAB, this gives you the matrices in ABCD matrices. And you could also do LaTeX, where it gives you the LaTeX code to copy and paste into document. So it's pretty nice. You can save it. I'll save this with a photo of the analysis as I did it, and then I'll send it out to you guys.
The latex code, do you have to put it into like put it inside $signs or whatever for it?
Yes.
Okay, small question. Are you ever going to have us do anything like that by hand?
Not on a test.
Yeah, no, like the homework problems are fine because
Yeah.
you use the program.
Because you have, and you can use a program, which is totally fine, or you have a long time to work on it. So.
The long time is not.
I didn't quite get down all the